So right now, today what we're going to do is inverse of a function. So basically you've done reflections over the x-axis. You've done reflections over the y-axis. Inverse of a function is a reflection over the y equals x line. So we'll illustrate that today, okay? It's just another reflection. The inverse f of x is denoted by f uppercase -1 of x. Okay? This is the symbol for inverse. Do not confuse this with a negative exponent. F -1 of x does not equal 1 over f of x. Okay? This has nothing to do with reciprocal. This is the symbol for inverse. What does an inverse do? The inverse of a function undoes what the original function does. Okay, so it brings you back. You have a point, you have a function that does something. The inverse is another function that brings you back to the original point. For example, if f of x equals 3x minus 4, the usual order of operations is we first multiply x by 3 and then we subtract 4. That's just following Bedness, right? The inverse f minus 1 of x equals x plus 4 over 3 means we first add the 4 to the x and second we divide the sum by 3. Notice that the operations on x are reversed in the inverse. The functions are inverses because one function undoes the other. Also note that f of 1 equals minus 1, and the inverse of f of minus 1 equals 1. So the inverse brings us back to what x was. It undoes what the original function did. So a function f has the inverse function f defined by the inverse of b equals a if f of a equals b. So what happens is your original function assigned a value of b to a, and the inverse takes that b and brings it back to a. It undoes what the original function did. How do we get it? The inverse of a relation is obtained by interchanging the components of each of the ordered pairs. In other words, the x and y values are switched. The domain of f of x becomes the range of the inverse f of x, and the range of f of x becomes the domain of the inverse of f of x. And we'll illustrate that with examples because I think just looking at it verbally is hard to see. In other words, for the point xy on the graph of f of x, there's a corresponding point yx on the graph of the inverse. So this point is the inverse of that point. As I mentioned before, the graph of the inverse function f of x is a reflection of the graph of f of x in the y equals x line. Points that lie on the line y equals x are invariant because their x and y coordinates are equal. For example, points such that 1, 1, 10, 10, minus 5, minus 5, then become the points 1, 1, 10, 10, minus 5, and minus 5 under the inverse operation. And I'll illustrate that with an example. The function and its inverse are congruent and symmetric about the y equals x line. They're identical in shape, they're just flipped over the y equals x line. Sometimes the inverse may not be a function. Okay? If f of x is a one-to-one function, then its inverse is a function. To be a one-to-one function, it has to pass both the vertical line test and a horizontal line test, and I will illustrate that to you in an example. Sometimes if we want to ensure that the inverse function f of x is a function, we restrict the domain of the original function to ensure its inverse is a function. Okay, so there's a lot of things there, and I will just illustrate everything with an example. So let's do as many examples as we can today. Okay. For each of the following functions, perform the following. Find the inverse algebraically. Note it, we do this by interchanging x and y, then solving for y. We're going to graph both the original function and its inverse and the y equals x line. We're going to find the domain and range of f of x and its inverse. We're going to determine if the inverse is a function. If it's not a function, we're going to restrict the domain of f of x so its inverse is a function. So let's just slowly go through all of that so it's clear. Here's our original function. So the first thing we're going to do in part A, we're going to find the inverse. There's plenty of room here, so we don't have to worry about running out of space. But in part A, you have your function f of x equals 3x plus 5. And I want to find the inverse algebraically. So it's cumbersome to work with f of x. So right now I'm just going to replace f of x with y just to make my computations a little bit easier. Now, what we do is we interchange x and y. X equals 3y plus 5. Right? So all I did was interchange x and y, and now I need to solve for y. So 3y equals, I'm going to move that 5 over there, x minus 5, y equals x minus 5 divided by 3. If you want to take it a step further and write it like this, that's fine. I will accept both answers. So now I'm going to write the inverse of my function f equals x over 3 minus 5 over 3. That is my inverse function. B. Now let's graph both these functions. Okay, let's do it. Now, the original function is a straight line. You notice that before we do anything, let's label these. Okay, just put our arrows on there, make it complete. Now, my y-intercept is 5, right? So I'm going to draw that when x is 0, y is 5. 1, 2, 3, 4, 5. My slope is 3, so for every 1 it goes over, it goes up 3. 1, 2, 3. Or if it goes this way, the slope is positive, so it's upward, rising upward to the right. If I go left, it's down 3, right? For every 1 it goes in a positive direction, it goes up 3 in a positive. 1 over, because the slope is really rise over run, which is 3 over 1. And I'm going to just draw another point here, right? 1 over up 3, 1 over, that's the slope of 3. So I'm just going to draw that. I think I want a longer straight edge. This guy's kind of short. Okay, here. So there's my f of x. Okay? Now I want to draw the y equals x line, right? Because it says draw the graph, the inverse, and the y equals x line. So let's just, y equals x is when x is 0, y is 0, x is 1, y is 1, x is 2, y is 2, x is 4, y is 4. When x is negative 4, 1, 2, 3, 4, y is negative 4, 1, 2, 3, 4. I'm sorry. Here, I'll put this up. Thank you for pointing that out. So I'll just draw this guy here. There's my y equals x line. For the y equals x line? Okay. You can do a table of values. You do what's easier for you. For the y equals, when x is -4, y is -4. Because they're equal, right? On the y equals x line, they're equal to each other. When x is 0, y is 0. When x is 4, y is 4. Okay? There. Okay. So now we want to do the inverse. Now this is a messy inverse. I don't like it. Why don't we pick some easy points to graph it? The easiest way to draw the inverse is, notice that this point is 1, 2, 3, 4, 5, 6, 7. Do you notice this point is 1, comma 8? Let me just double check that. 1, 2, 3, 4, 5, 6, 7, 8. Right? So the inverse would be 8, 1. Because the x and the y is switched. 1, 2, 3, 4, 5, 6, 7, 8, 8, 1. The inverse of that point is here. Okay? This is 8, comma 1. Now, this point here is, let's do another point, just to really help us out here. This point here is 1, 2, 3, -3, comma 1, 2, 3, 4, -4. So the inverse will be -4, -3. So 1, 2, 3, 1, 2, 3. I'm just double checking. So our inverse will be negative because the x and y get switched, right? So this is 1, 2, 3, 4, 1, 2, 3. Let me draw that maybe with a blue line. So I am just going to draw that right now. Okay, so this is our inverse function. Oh, you know what I forgot to do is write f minus 1 of x. I should have a minus 1. This one is f minus 1 of x. And there, now we've drawn both graphs. Do you notice any point that lies on the y equals x line is invariant? So that point stayed right where it is. Okay, that when you do an inverse of a function, and an inverse is just a reflection over the y equals x line, any point on the y equals x line which is there stays there. It's invariant. It didn't move. So let's now do part C. I did part B. Part B was the graphs, right? There's our part B. Let's do part C. We have we'll do the domain of f of x. We'll do that here, domain. And then we'll do the domain of the inverse, which the domain of a straight line is x can be anything, x such that x is an element of real numbers. And the range is, well, y can be anything, y such that x is an element of real numbers. F minus 1 of x for the inverse. Well, the domain of f of x becomes the range of the inverse. So we will write y such that y is an element of real numbers, right? The range of the original function, the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. inverse. So this is going to be x such that x is the element. So you can't see it here because it's xer. That should be yer. Yeah, okay, that's better, right? Can you tell me, is the inverse a function? The inverse, which is the blue line, passes the vertical line test. So d f minus 1 of x is a function, so we don't have to worry about restricting any domain on the original function. So that was a simple example. Now we have to do a harder example. Okay? Do you notice if I were to fold this paper along the y equals x line, those two lines would end up on top of each other? Right? If I did some folding here. Okay, let's go on. Are we good? Let's do at least one more. Yep. Yeah, you can. Okay. F of x equals 2 times x plus 1 all squared minus 3. Now we're going to do the inverse of that one. So that one's a little bit harder. Okay? A. Find the inverse algebraically. We have the original function is f of x equals 2x plus 1 all squared minus 3. Now to make it easier to work with, because the f of x can be a bit cumbersome, I'm just going to use y for now. Now we're going to swap the x and the y and then solve for y. So I'm going to add, I need to solve for y. I'm going to add 3 to both sides. X plus 3 equals 2, y plus 1 squared. Now I'm going to divide by 2 because I'm trying to work my way toward that y so I can isolate it. Let's get rid of the 2, so we'll divide both sides by 2. So we have x plus 3 over 2. 2 divided by 2 is 1, so we have y plus 1 all squared. So I'm just going to rewrite it like this because you want your y to be on the left-hand side. I just rewrote it, right? I'm going to take the square root of both sides. So square root of y plus 1 all squared is just y plus 1. And remember, you have to take the plus or minus square root of x plus 3 over 2. So y equals minus 1 plus or minus square root of x plus 3 over 2. And we can leave it at that. So f minus 1 of x equals minus 1 plus or minus square root of x plus 3 over 2. And if you wanted to simplify it further to rationalize the denominator, we could, because notice we have a square root of 2 on the bottom. This is going to be negative 1 plus or minus square root of 2 times x plus 3 all over 2. And we could even say negative 2 plus or minus root 2 times x plus 3 all over 2. So this is f minus 1, the inverse function. So let's now graph this algebraically. Let's now graph it. We've done it algebraically, let's now graph it. Okay. So now we know the vertex is negative 1 minus 3. Negative 1 minus 3, that's a good starting point. Our y-intercept is, let's just use a few points here to save ourselves some work. Our y-intercept occurs when x equals 0. 0 plus 1 is 1. 2 minus 1 is 2 minus 3 is minus 1, so we have a point there. I'm just subbing in values. If x is 1, 1 plus 1 is 2, 2 squared is 4, 2 times 4 is 8, 8 minus 3 is 5. 1, 2, 3, 4, 5. And the rest of the points I'm going to use by reflection. So here's my axis of symmetry. I know I have a point there, and I know I have a point, let's see, there. Yes. That's something you should do, but let me get back to you. I'll see what, once I'm more familiar with the test, we'll just see if rationalizing the denominator is important there. Sometimes we allocate marks to it and sometimes we don't. So, but I'll let you. Yep. Negative 2 where? Here? Here? Well, I put it all on the same denominator. So negative 1 is the same as negative 2 over 2. I've just got a common denominator. That's all I did. So there's my parabola, my original. There's my f of x. Let's draw in the y equals x line. Okay? The easiest way to draw the inverse is we're going to take these points, swap the x and y, right? So my vertex is negative 1, negative 3. So my inverse will become negative 3, negative 1. 1, 2, 3, minus 1. This point here is 0, 1. My inverse will become 1, 0. This is 0, minus 1. My inverse will become minus 1, 0. This is 0, minus 1. My inverse becomes minus 1, 0. Right? We just swap the x and y. That's all we have to do. This point is negative 2, negative 1. My inverse becomes negative 1, negative 2. So that's right here. A little bit tight there, so be careful. I'm trying to be careful. This point is 1, 5. 1, 2, 3, 4, 5. Maybe my inverse, this is 1, 5. My inverse is 5, 1. 1, 2, 3, 4, 5, 1. This point is negative 1, 2, 3, negative 3, 5. My inverse becomes 5 minus 3. 1, 2, 3, 4, 5. 1, 2, 3. So I'll just draw that in right now. You just bear with me and I'll put it back so you can see it. There's my inverse. So you take the original point, swap the x and y, and that's probably the easiest way to do that. So we did part B. Now we want to do part C, which is find the domain and range. Okay, we'll do f of x first. Domain. So, on a parabola, you know domain is x such that x is an element of real numbers. Our range is anything it's bigger than or equal to -3. So, now, the domain of my original function, the range of my original function becomes the domain of the inverse. So what we're going to write is x such that x is greater than or equal to -3. X is an element of real numbers. And our range becomes the domain of our original function. So y such that y is an element see how the -3 went there and all real numbers went there. Do you see how they swap? Now, part D, I believe it's part D, is the inverse of function. Notice it does not pass the vertical line test. Right? See here, there's such a thing as a horizontal line test. See how it does not pass the horizontal line test? If I draw a horizontal line through here, I hit 2 points, right? So the inverse, I'm going to hit 2 points at as well. So the inverse is not a function. How do we restrict the domain of the original function so the inverse is a function? What should we do? Well, the issue is this has 2 branches. What we want to do is just get 1 branch. Do you notice that this branch here is the inverse of that branch? Right? Can you see that? Because this point here is 1, 5, and that's 5, 1. So this branch is an inverse of that branch. And this branch is an inverse of that branch, because that's -3, 5, and the point 5, -3 is here. That point is coming down there. So what we want to do is knock off one of these branches, and it doesn't matter which one you do. We want to restrict the domain of this so the inverse is a function. So if I were to knock off this branch, that would knock off this inverse, right? So if I knock off that inverse, then I'll have a function that is, I'll have a function now. This inverse will be a function. So basically what you do is you can either knock off this half or knock off that half. So watch. So this is what we do. We restrict the domain so that if I knock off this guy, then I'm left with x is greater than or equal to -1. X is the element of real numbers. I can either restrict it to this, or I can knock off this guy and keep this branch. X such that x is less than or equal to -1. X is an element of real numbers. So it's either this one or this one. If I knock off the left branch, I'm using this restriction. If I knock off the right branch, I'm using and keeping this one, I'm keeping this restriction. Yes?
So I didn't understand, how did you find the points of inverse function?
Okay. My original function is here. So my original function, one of the points is 1, 5. So the inverse function, the point is 5, 1. So it's 1, 2, 3, 4, 5, 1. Here is -3, 5. So my inverse is 5, 3. 1, 2, 3, 4, 5, 1, 2, 3. Yes?
So every single time we have an inverse function, we always just flip the x and the y value.
What do you mean by that? You mean when you're graphing?
Yeah.
Yeah, when you're graphing, you just swap the x and the y.
Okay.
Yeah? Richard?
Why we have to solve it algebraically like that if all we do is just flip the points?
You want to be able to use both methods, both algebraically and graphically. Some of your questions, you need to be able, you're kind of asking, well, why, if I can graph a function, why do I need an equation, right? You know, you want to be able to represent an inverse function both algebraically and graphically.
Will we always be able to graph it that way?
Yes. Where you just swap the points? Yeah.
How would you do it with the equation?
Oh, that's harder because you have to sub in 0 and find,
You might have to do that on like a
no,
test. Okay. We still have to find it.
yeah. You'll have to be able to use both methods. Yes?
How do you know for the restrictions, how do you know whether it's less than or equal for x?
It's either one. You can pick either one, okay? If the question asks you restricts the domain of the original, so the inverse is a function, you either pick greater than or equal to 1, or you pick x is less than or equal to 1. Either one answers the question.
Why is it 1?
-1, because that's what cuts the graph in half, right? When x is, the equation of the axis of symmetry is x equals -1. So it's either less than that. Yeah. Good.